To automate the process of assembly line in manufacturing, we're working on robotic bin picking. It refers to picking up parts individually from a container where parts are randomly placed. Robotic bin picking using wire harnesses, which usually have complex geometries with bundles of cables and rigid connectors, is an important topic for automation, but is also extremely difficult. Wire harnesses pose challenges in bin picking. First, physical phenomena in heavy clutter are complex. They are also easily entangled with each other. Manipulating such long and flexible objects is still an open problem. Motivated by human picking strategies, this work tackles the bin picking task using wire harnesses by two key ingredients. First, instead of lifting in the vertical direction, the robot separates the entangled objects in the horizontal direction, following a circle-like trajectory. Second, we learn a policy that enables the robot to pick following a reasonable sequence. It prioritizes grasping the entangled objects and inferring the disentangling actions from observation. We propose two disentangling motion primitives imitated from humans. Helix motion can disentangle the objects softly from a clutter along a side angle. Spinning motion can quickly discard the entangled objects. We plan 6 discrete actions using the combination of two motion primitives and evaluate their performance. To reduce the search cost during exploration, we assume a linear relationship between actions and their success rates. We use this linear relationship to experimentally predefine the execution parameters of each action, such as the trajectories of the helix motion, or if the spinning motion is needed. We also assign integers 0 to 6 as action complexity, which linearly scales with the success rates. Given the depth image of the cluttered objects, Model-Free Grasp Detection Module samples a set of non-collision grasp candidates. Then, Action Success Prediction Module, ASP.NET, takes the depth image, grasp candidates, and action candidates as input, and evaluates the success possibility for each action grasp pair. Finally, Action Grasp Selection Module ranks these pairs and outputs the best grasp and action. Since wire harnesses are difficult for modeling or simulated training, we collect data in the real world to train ASP.NET. To reduce the cost of human intervention in data collection, we executed each action and record if the robot can isolate the entangled wire harnesses, and leverage active learning to adjust the labeled action complexity. For example, action complexity of 6 can successfully disentangle the object, but we prefer action complexity lower than 6, which can save time. On the other hand, we prefer higher action complexity to solve the failure cases. Next, we leverage active learning to train the ASP.NET. Generally, we first select several samples manually as training data to train ASP.NET. Use the trained ASP.NET to predict the remaining samples, query and add samples to fine-tune ASP.NET repeatedly. Label evaluation continuously adds logical samples to training data. For example, success picking samples with lower query action complexity are added, or failure picking samples with higher action complexity. At this point, we've obtained a set of grasp candidates, action candidates, and the scores of each action grasp pair. Our policy then needs to determine which action grasp pair can be executed. This module infers the best action grasp pair to guarantee a successful picking with minimal action complexity. In active learning, we stopped training after 3 times of fine-tuning as it achieved the best performance. We also validate the performance of the final model of ASP.NET. It can predict the optimal actions compared with the labeled one. We compare the bin picking performance of our policy with the baseline. Our policy can significantly increase the average success rate. The PPH also shows the efficiency of our policy. We also use bins filled with different number of objects, demonstrating that our policy can handle various entanglement patterns. We also test our policy on a novel type of wire harness. It is different in length and structures, but has similar components. Here's a video showing the consecutive picking task. Our policy can select relatively simple actions under the current observation and ensure a safe picking without entanglement. For more details, please check our paper or the web page. Thank you for watching.